Okay, folks, let's go ahead and keep working with this. I'm now looking at example number 3. A circle's radius is increasing by 1 foot per minute. How fast is the area increasing when the radius is 5 feet? And then the next question is, how fast is the circumference increasing? So there's two questions here. Maybe I should have separated them, but I'd like you to focus on this first one. So go ahead and give this a shot. Pause the video and try working it out, and then come back and we'll see how we did. Okay, folks, let's resume. Hopefully you had a chance to try it. If you got it, that's awesome. If not, let's give it a shot here. So first step, well, let's draw a picture. So here we've got a circle, and what's happening with this circle? Well, the radius is increasing, right? And so as the radius increases, so does the area of the circle, so does the circumference of the circle. The question is we know that the radius is increasing by 1 foot per minute. How fast is the area increasing? So we said, okay, step 1, come up with a formula that relates everything together. And here again, these have all sort of relied upon your geometric knowledge. Area of circle is pi r squared. The next few problems, so they're a little bit more difficult because the formula that relates everything together isn't quite as clear as this. So we've come up with the formula. That's actually the hardest step. Then we implicitly differentiate both sides with respect to t. So that gives us dA dt is equal to pi times 2 times r times dr dt. Okay, remember, pi is just a constant. It comes along for the ride. What's the derivative of r squared? Well, it's 2r, but then by the chain rule, we have to multiply that by dr dt. So let's start plugging in what we know. Well, pi is pi. That's the constant 2. And we're asked, when the radius is 5 feet, how fast is dA dt changing? So we're going to input a 5 here. And we know that the dr dt is 1, so we input 1 for dr dt. So this gives us that dA dt is equal to 10 pi, or approximately 31.4 feet squared per minute. Okay? So specifically, when the radius is 5 feet, dA dt is the area is increasing by 31.4 feet squared per minute. Now, as the radius gets even larger, the rate of change of the area will continue to increase because of this r factor here. Okay? So, if you haven't, go ahead and try the second question. So, pause the video and try the question: how fast is the circumference increasing? And I'll work it here in just a minute. Well, the formula for the circumference of a circle is 2 pi r. Implicitly differentiating both sides gives us that dc dt is equal to 2 pi dr dt. So that tells us that dc dt, what we're after, the rate of change of the circumference of the circle, is equal to 2 pi times 1. Now, how is this different from the last example? In the last example, notice that there was a still lingering factor of r here. So we had to include the fact that the radius was 5 feet for the instant that we were interested in over here. Notice that the way that c and r are related means that it doesn't really matter what the radius currently is if we ask the question, how fast is the circumference changing? Because there was no factor of r that showed up in here, only dr dt. That's kind of interesting. It shows that these are sort of two completely different level of these two questions are two completely different levels as far as their interrelationship between their rates. So anyway, we get that dc dt then is approximately 2 pi, which is approximately approximately 6.3 feet per second. So when the radius of a circle is changing, oops, I made a mistake there, folks. That should be feet per what? Yeah, that should be feet per minute. Careful with that. So that says that as the radius of a circle is increasing by 1 foot per minute, we would expect the circumference to be increasing by a factor of 2 pi, meaning 6.3 feet per minute.